Now recording, sir.
Okay. Are you able to see my PowerPoint?
Yes, sir.
Good morning, friends. I'm going to give you a lecture on binding energy and stability curve. This is my outline of my talk. I'm going to give an introduction about the binding energy and definition of binding energy, what is most effect, and binding energy, how to do the binding energy calculation of lithium nuclei, what is mean by binding energy per nucleon, and then what is stability of curve, and what is the how the stability curve is increases and decreases for a lighter and heavier nucleus, and which one is the maximum nuclei for nuclei having binding energy per nucleon, and finally we discuss with some conclusions. So first, introductions. To learn the concept of binding energy, we have to study the Albert Einstein's relativity principle. He says that mass and energy both are convertible. Any mass can be considered as energy, or any energy can be considered as mass. That means we can convert the energy into mass, and same way we convert the mass into energy, by which formula there is an equation, the so-called Albert Einstein's theory of relativity. He says that E is equal to mc square, that is E del mc square, where E is the binding energy, del m is the mass defect, and c squared is the speed of light. So the definition of binding energy is required to separate a nucleus into individual protons and neutrons, or energy released when nucleus is formed from its individual nucleons. So what is mean by mass defect? The nucleus of each atom has mass lower than from the adding of mass of proton and neutron. This is known as mass defect. As I know that the nucleus consists of protons and neutrons, it may be expected that mass of nucleus will be the sum of individual proton mass and neutron mass. For example, suppose suppose a mass of proton, your individual mass of proton is 10 and our individual mass of neutron is 10. If we add together proton neutron, the sum comes to 20. But where the whole nucleus, the complete nucleus, if you measure the mass of the nucleus through mass spectrometry, the mass of the nucleus is always less than the mass of the proton and mass of the neutron. It is found to be 18. So the mass of individual proton and individual neutron is 20, but complete mass, that is means actual mass of nucleus is 18. So what is this difference? The difference is 2. We combine to form the nucleus, the value is 18. So where this 2 goes, this 2 is converted into energy. So it is very interesting that the difference 2 is called mass defect. It is denoted by del M. So now we are going to solve one binding energy nuclei of lithium, and also we calculate binding energy per nuclei. So this is our formula. Mass defect del M is equal to ZMP plus A minus Z Mn minus capital M. So del M is the mass defect, Z is the atomic number, that means the number of protons. That A minus Z is the A is the mass number, and minus of atomic number, it gives the number of protons, and capital M is the actual mass of the nuclei. So you know that mass of proton is 1.00782 A atomic mass unit. Mass of neutron is equal to 1.00866 atomic mass unit. So now we find mass of lithium. The mass of lithium, this is 3 is the atomic number, 7 is the mass number. So the whole mass of lithium is 7.015 double nine atomic mass. This will be found from the mass spectrometry. Now, what is the formula? You substitute the formula del m is equal to Z, number of protons in the lithium for 3. So 3 into mass of proton plus how much of mass of neutron? 7 minus 3 is 4. 4 is the neutron number. 4 into mass of neutron minus of whole mass of the lithium. So we substitute the 3 into mass of proton, how much? 1.00782 plus 4 into mass of neutron and minus of a whole mass of the lithium. So if you multiply this and adding with this, it comes 7.0581 and minus of 7.0159 for whole mass of the lithium. So what is the difference? The difference del m is equal to 0.04211. So the loss of mass, that is mass defect del m, is equal to 0.04211 unit. So one atomic mass unit is equal to 9.31.5 mega electron volt. One atomic, we know that one atomic mass unit is 9.3. So in terms of, we find in electron volt, the binding energy formula is del m into this is you put the 9.315.5 mega electron volt, and we get the binding energy of the lithium is 39.225 mega electron volt. So we found the binding energy of lithium, but and also we like to calculate the binding energy per nucleon. So what is the binding energy per nucleon is obtained by dividing the binding energy of the nucleus by the number of nucleons or mass number it contains. This is the binding energy formula. The binding energy formula is binding energy per number of nucleons or mass numbers. So what is the binding energy for lithium? 39.22 mega electron volt divided by what is the mass number? This is 7. So I divide it 7, we get 5.06 mega electron volt. This is so 5.06 mega electron volt for binding energy per nucleon of lithium. So now you understood how to calculate the binding energy of the nuclei of the given nuclei, and also you learned about the binding energy per nucleon. Now this is the table shows some of the lighter nucleus some of the lighter nucleus to heavier nucleus shown in the left hand side, and knowing the mass of the nucleus or mass of the atom binding energy per nucleon of the nucleus can be easily determined. So the value of these two quantities, that is binding energy and binding energy per nucleon, are calculated and tabulated in the in this table. So every nuclei having binding energy and binding energy nucleon. This is hydrogen for binding energy, and this is binding energy per nucleon. Like that, the lithium, chlorine, iron, bismuth, uranium, we have calculated for binding energy and binding energy per nucleon. But it is interesting to see that you see that lithium having the very lighter nuclei, they are having the binding energy is 37.66 mega electron volt is greater than the helium, So what helium? But when you see the binding energy per nucleon for helium is 7.08 mega electron volt, which is higher than the lithium. So what you found from this table, helium is found to be more stable than lithium. So the stability of the nucleus depends upon the binding energy per nucleon rather than the binding energy. So therefore, the knowledge of binding energy nucleon of a nucleus is more important than its binding energy. So this is the graph. Graph is plotted with the binding energy binding per nucleon in mega electron volt along the x-axis and mass number along y-axis. Mass number x-axis. So it is found that binding energy per nucleon varies from element to element, varies from element to element. See, this the binding energy of a lighter nucleus such as hydrogen is very small. See that the binding energy of binding energy per nucleon hydrogen is very small, and the binding energy per nucleon is increases rapidly for nuclei up to mass number 20. So up to mass number 20, this is the mass number 20 in the x-axis. We take the one line. This mass number 20, the lighter nucleus is increases further and further, uh, and the curve possesses peaks corresponding to nuclei, helium, beryllium, and carbon and oxygens. These peaks indicate these nucleus are more stable. So this is the helium, this is carbon and oxygens having a more stable rather than the neighbor nucleus. It is another one interesting to see that the nuclei such as helium, beryllium, and carbon and oxygen, whose mass number are multiplies of 4, that means they contain equal number of protons and equal number of neutrons. See, this is the helium, this is the carbon, and this is oxygen. The mass number is multiples of 4. 4. So is having sharp peaks in the binding energy per nucleon curve, whereas the neighbor atoms such as lithium is dropped some fluctuations in the binding energy per nucleon around lithium around mass number 6 and 7 and mass number 14. So why this the curve is fluctuations in the neighbor atoms means the equal number of mass, equal number of protons and equal number of neutrons and in contributing the helium and carbon oxygen having more number of which is more stable than the neighbors lithium and nitrogen. So after mass number 20, the binding energy per nucleon increases rapidly, and mass number between 40 and 20, the curve becomes flat. So after mass number 20 is sharply increasing, and after 40 to 60, the 120, the curve is more or less flat. So the curve rises sharply at first and then more gradually until reaches 8.8 mega electron volt. See, so after that is a small short peaks and increases up to 8.8 mega electron volt for iron, which is found more binding energy per nucleon. So this is the most stable nucleus among all the nuclei in the curve table. This is 8.8 mega electron volt is the most stable nucleus among all the nucleus. After that, see what happens. It is found that average binding energy per nucleon is 8 mega electron volts, whose mass number ranges from 40 to 120 are comparatively more stable. Hence, the stable nuclei is non-radioactive. See what this is in this curve. The average binding energy per nucleon is 8.5 mega electron volt. So whoever the nuclei having average binding energy per nucleon 8.5 mega electron volt, which is false, the mass number range 40 to 120 are more stable. Hence, the stable nucleus non-radioactivity. So what I'm going to tell another one important point here. After mass number 20, the binding energy per nucleon start decreasing. See, after mass number 20, the binding energy per nucleons start decreasing. So and it drops to 7.6 electron volt for uranium. It 7.6 mega electron for uranium, whose having mass number is whose uranium mass number is higher mass number, but it is which is very unstable. This is due to Coulomb's repulsion between the large number of protons Such nuclei are unstable and found to disintegrate by emitting alpha particles. Hence, unstable nucleus is radioactive. I want to I like to one important criterion for stability of nucleus is means that stability meaning that the stable nucleus does not emitting the spontaneous emission of radiation. So the stable nucleus always not emitting any kind of radiation spontaneously. That nucleus are very stable. That is called non-radioactive nuclei. Whereas some of the radionuclides having emits radiations in the form of emitting radiation in the kind of it's that is called radioactivity is associated with unstable nucleus. This is the one of the important point I like to mention. Then another one in the uranium for why the alpha particle is emitting here means the low value of binding energy of nucleon in case of heavy nucleus is unable to control over the Coulomb's repulsion between large number of protons. Large number of protons. Such nuclei are unstable and found to disintegrate emitting alpha particles. So an alpha particle in a nucleus of helium has 2 protons and 2 neutrons. The emission of alpha particles not only decrease the Coulomb repulsive force inside the nucleus, but also increase the value of binding energy per nucleon of the nucleus to its extraordinary stable structure. It is called alpha decay. Sometimes a heavy nucleus increase the value of other binding energy per nucleus by emitting an electron. It is called beta decay. Inside the nucleus, an electron does not exist. It is created at the time of beta decay due to the conversion of a neutron into proton. The beta decay leads to increase the Coulomb repulsive force, but increases binding energy per nucleon and also improve the neutron proton ratio. So all such nuclei which undergo alpha decay and beta decay are called radioactive nuclei. So binding energy per nucleon has a low value for both very light and very heavy nuclei. For example, helium and uranium. In the table, we see that the helium, the low value for value for binding energy per nucleon, and very high value of uranium. It shows that very light and very heavy nuclei for one of the examples. In order to attain the higher value of binding energy per nucleon, the lighter nucleus unit together to form a heavier nucleus. This process called fusion. So in order to attain higher value of binding energy per nucleon, some of the lighter nuclei may unite together to form a heavier nucleus. This process is called fusions. On the other hand, a heavy nuclei may split into a lighter nucleus. A heavy nuclei may split into lighter nuclei. This process is called nuclear fissions. In both nuclear fission and fusion process, the resulting nucleus occurs greater value of binding energy per nucleon along the liberation of energy. So now I like to tell another one important point to mention that the stability of the nucleon is also determined by its neutron to proton ratio. In general, for stable nuclei, neutron proton ratio should be greater than 1. So apart from the higher value of binding energy per nucleon and a proper neutron proton ratio, the stability of the nucleon is determined by the consideration whether it is an even nucleon. That means even number of protons and even number of neutron, or even at nucleus. That means even number of protons and odd number of neutrons are odd even nucleus. That means odd number of protons and even number of neutrons are odd nucleus. That means odd number of protons and odd number of neutrons. So in this the four possibility in the four point of consideration, the even nucleus is more stable, even it has low value of binding energy per nucleons. So in the conclusion, the nuclear stability in the periodic table, as this concept, and the periodic table, we found that 168 nucleates, 16 in the periodic table, 168 nucleates having even number of protons, even number of neutrons, which is more stable. Then 57 nucleates having even number of protons and odd number of neutrons, which is more stable. In the same periodic table, the 50 nucleates having odd number of protons, even number of neutrons, which is less stable. In the periodic table, only 4 nucleates having odd number of protons, odd number of neutrons, which is less stable. In this binding energy per nucleon, nuclear stability, it depends not only not only the binding energy and also binding energy per nucleon, and also the binding energy per nucleons whose mass number multiples of 4 also having, even the light nucleates having higher binding energy, higher stability than heavier ones. And also the nuclear stability also another one important criterion for nuclear stability for radioactive element and non-radioactive elements. Those elements emitting radioactive material, this is unstable. Those nucleates not emitting any kind of spontaneous radiation, that's called non-radioactive, which is more stable, which is which falls around 40 to mass number 40 to 120, which is having the average binding energy per nucleon is 8.5 mega electron volt. And another one important, in order to increase the binding energy per nucleon do by nuclear fission and nuclear fusion process also. Then last one, final criterion for nuclear stability is neutron-proton ratio. So not only the neutron-proton ratio, and also if a proper neutron-proton ratio, whether the even number of protons and even number of neutrons, which is the most stable than the even number of protons, odd number of neutrons, and odd number of protons and even number of neutrons, and finally odd protons and odd number of neutrons. Anybody having any doubts in this lecture? Hello students, any?
No, sir.
No, sir. Thank you. Thank you so much. We finish this lecture today, and we go for next topic in the next lecture. Thank you. Thank you, students.
Sir, lobby